Hello, everyone. It's me, and today I will talk about deep diving to Kubernetes Runtime Security and see the technologies and techniques we can keep our containers secure while they're up and running. I'm a founder of KubeArmor.io, and at KubeArmor, we delivering training courses for Kubernetes and any Kubernetes-related tools and technologies. Today, our agenda is what is runtime security and deep dive into tools, modules, and technologies within the Linux kernel provide us the security stuff and how we can use them within the Kubernetes. And then we go through the KubeArmor, which is a CNCF technology related to keep your containers secure while they're up and running. You can scan our LinkedIn and follow us if you want to start your Kubernetes journey. What is runtime security? What is runtime security at all? It means you want to protect your application when the application is up and running. In the case of security for the application, we can secure our application at two stages. Pre-runtime and at runtime. The pre-runtime means you scan your application through static analysis and anything related to code and find the well-known vulnerabilities. But at the runtime, we want to mitigate and prevent zero-day attacks and prevent malicious behavior within our application. So we need to respond to the threats dynamically and block or mitigating attacks. And in the case of runtime security, it's done through real-time intrusion detection and preventing the intrusions and attacks through process isolation, enforcing policies, providing and implementing some access controls, and monitoring the application behavior. And in Linux, we've got a couple of in-kernel features, and we can use some external security features as well. The goal of runtime security, as I said, is to prevent zero-day attacks, because there is no way to find them pre-runtime in our pre-runtime environments through static and dynamic tests. In Linux, the security features you may know is SELinux, AppArmor, Linux capability, Seccomp-bpf, permission, and ACLs, namespace, and cgroups. But the fact is, in Linux kernel, we have at least 30 mechanisms to secure your kernel itself and the application. And the Linux kernel developed some drivers to support hardware-level security, as well as some security layers to protect memory-level attacks, just like preventing meltdown and Spectre attacks. And some of them needs to be enabled during the boot time. I skip these technologies which exist in the kernel because it's too much. I just bring them here to provide you a reference, and you can dig into and check what's going on and which feature is available within the kernel, and you can enable, and what is the purpose, what is the summary. And today, I want to go through the well-known features like Linux capability, Seccomp-bpf, LSM modules, and a couple of other well-known security features. What is Linux capability? Prior to Linux capability, when we run an application within a Linux environment, we had two types of process, the privileged process and unprivileged process. The privileged process was a process with all the capabilities. Just like a ping command, if you back to old Ubuntu systems or Red Hat systems, the ping application had all the capabilities that the root user had, which means when some person tries to ping a website or a domain, based on using the set UID and the set GID bits for that process, for the application, the user was able to grant the privilege, which caused to be able to bypass the routine. There are a couple of exploits within the market back to Ubuntu 12.4. And it will enable the user to use the ping command to escalate the privilege and then run the exploit. Because the ping command had all the root permissions. And because of that, the community started to develop some new feature known as capabilities to separate the privilege, to separate the boundaries of the capabilities we have within the kernel. So at the moment, when the user tries to do something which is harmful for the system, instead of gaining all the privilege, they go through the Linux capabilities, which can be set through a couple of commands. And if you check the process and get the status of the process, you can see there are a bunch of bits available for the process, shows the effective, permitted, the bounding set, and ambient and immutable capabilities. And then, with using the setcap command and getcap command, you can check what the capabilities exactly the application have. And in the case of ping, at the moment, instead of setting the set UID and set GID bit, you can see it's a normal application, but because of the capabilities and with the capabilities of Netra, this application is able to open a raw socket and ping your destination without going beyond the privilege you mentioned with the capabilities. The other solution to keep running process secure is using Seccomp and Seccomp-bpf. What is Seccomp? Seccomp, or secure computing, is a mode within the kernel to prevent the process from executing and calling the system calls, the normal system calls. The original Seccomp was designed to restrict a process to only be able to execute read, write, exit, and sig return functions within the kernel. And after some time, because of the need of container and the community, they start developing Seccomp-bpf. And at the moment, with the Seccomp-bpf, you can create a Seccomp-bpf profile and attach it to the process. And when the application is get up and running, and it tries to call a system call and invoke a system call, it goes through the Seccomp process, and the Seccomp checks if the process is able to invoke that specific system call. And if it's not allowed, then the kernel will terminate the process. The next security feature within Linux kernel is LSM, which provides a couple of hooks, which allows you to check what's going on within the application, within the process. LSM is a framework, provides a security model, and allows you to define the policies. They use hooks within the kernel to intercept the operation. For example, when I want to access a file, I can create a policy and get the function parameter, for example, the source, the destination, the source process, and the destination file, and check if that process can access to that specific file, or if the process can communicate to some IP address, if the process can bind a specific port, or do so. And the good thing about the LSM is the LSM modules work as a dynamically loaded modules, and you can load LSM modules without recompiling the kernel itself. And some LSM modules suppose LSM stacking, which means you can have more than one LSM at the same time and have all the best of these LSMs to secure your applications. And the LSMs are integrated into the kernel, and which each module provide and attach to a specific hood within the kernel to enforce and restrict the process from doing some malicious behavior. And this is the process when a user space process tries to invoke a system call and access something within the system, some resource within the system. The system tries to dispatch the system call, invoke the system call, and first the kernel checks for the permissions, and then it gets to LSM hooks. And using the LSM hooks, by using some enabled LSMs, SELinux policies, LoadPin, Yama, AppArmor, and any other LSM modules can check and verify if the process can access to the resource. If it's allowed, then it can, for example, manipulate the file. If it's not, it gets terminated. And this is the process in detail. My application tries to open the file. It goes through the DAC system, and then it goes through the MAC system, the LSM hooks. I want to open the file with fopen function, and then it's called the security file open, which is the Linux LSM hook. And that hook tries to check the next one, the next function, which is SELinux file open. And this function checks the policy and verify if the process is allowed to do so. And you can see the fopen goes to the LSM security file open. It calls this SELinux file open, and then check the policy, and then get back to the process again. At the moment, there are a bunch of LSM available within kernel: SELinux, AppArmor, SMAC, Tomayo, Yama, Landlock, and LoadPin. And they provide different ways of enforcing the policies for your process. For example, SELinux use a label-based model, but AppArmor is provide a profile-based or path-based model. So it's up to you to choose which LSM should be used. But in fact, SELinux and AppArmor is the major ones in the market. And if you want to compare them, you can check it out. Why not SELinux? It's because life is too short for SELinux. It's really, really hard to learn and implement SELinux profiles. There are a bunch of tools like audit to allow, which capture the process behavior and provides a profile for you, but it's not useful within the containers, and it's not useful when you have a bunch of applications running in a Kubernetes cluster across different nodes. For a normal application deployed in a single node, you can run audit to allow command, and then you can create a profile. But at scale, it's really hard and it's a big pain. The other solution is a BPF LSM, which is quite new. And BPF LSM allows us to inject eBPF bytecodes into LSM hooks instead of using AppArmor, SELinux, or other solutions, we can use eBPF bytecodes. And the good thing is it's completely stackable, which means you can have BPF LSM in addition to your AppArmor, your existing AppArmor LSM or SELinux. And because we're using the codes for the BPF, it provides us more flexibility than the other LSM modules. And the good thing is, with the BPF LSM, you can change the policies on fly without restarting the application or rebooting the system. It depends what you want to do. But with AppArmor, with SELinux, with other LSM modules, you need to restart the application to reload the new profile. But with using the BPF LSM, you don't need to restart that. And the drawback and the main issue with the BPF LSM is it's available in kernel version 5.7 and later. It's not available in previous versions. And the architecture is something like this. We have an application process. It tries to access a file and invoke a system call. And instead of using AppArmor, we have some bytecodes, eBPF bytecodes, injected to LSM hooks. And then it can manage everything for us. Runtime security in Kubernetes. The runtime security in Kubernetes refers to using the techniques and technologies to protect your pods and containers from malicious behavior while they are up and running. How we can use Linux capabilities in Kubernetes is quite easy. You need to provide some sort of configuration in your manifest. For example, within this manifest, I dropped all the capabilities. And when I try to do something within the container, even though I'm using the root user, I have no access to run the chown command, chroot command, or any other actions need some capabilities, even though you're running your container as a root. And if you check the container default capabilities, these are the default capabilities when you create a container without specifying any capabilities. The next thing is Seccomp-bpf, which is quite easy again. You need to define a JSON file within var-lib kubelet seccomp. And I defined a strict policy here to allow to deny everything except read, write, exit, and sigreturn to provide an example for you to restrict everything. And then I can use a seccomp profile within the security context. And because at the moment, the main process of the container is completely restricted from invoking any other system calls, you can see the container is being created, and it's never up and running. It's because of you need to find which system calls your application needs to invoke. Other than your pod will not come up. AppArmor in Kubernetes. The next one is the AppArmor, which is quite easy again. You need to connect to the worker node, define your policy. For example, I have a sample policy here, which provides some sort of access to files, network, and I can deny file access, network access, or anything related, and can be defined within the AppArmor profile. And within this example, I denied access to shadow file, passwd file, and deny executing the sh and allow the application and the process to access all the files within www.html directory and be able to execute the nginx command. And when I deploy the application, the nginx container, if I try to access these specific files, it shows me the permission denied. Even though I'm a root user, I have access to the file system, I have access to everything, but because of the AppArmor profile I used, I can access to these specific files. This picture provides you the threat metrics for Kubernetes. And as you can see, it's more than 50 items as a threat metrics in Kubernetes, and we are just talking about a couple of execution and privilege escalation metrics. And this one is the attack metrics for Kubernetes, which is quite more than 100 techniques attackers can exploit or bypass the system through these processes. In the case of Kubernetes threat detection tools, we've got lots of tools. And for the runtime security, we have Falco, Tracy, ThreatMapper, Tetragon, and KubeArmor. You can check the purpose and summary of each of them. And we've got a couple of other tools for static analysis, vulnerability scanners, SBOM or KBOMs, and security management platform like Trevi, KubeBench, KubeSec, and a couple of others applications. I'm not going through them, and I just want to go to drop to KubeArmor, which is a CNCF project, and it helps you to define the profiles with ACE. If I get back to this example, which is about my AppArmor example, writing AppArmor profile or SELinux profile is not easy, and no one wants to deal with that. KubeArmor provides a way to allow the user to define the policies through Kubernetes CRDs in a declarative mode, and it translates the CRD into AppArmor profile or SELinux. It's based on which LSM is available in the worker node. The other issue with running AppArmor profiles or SELinux directly in Kubernetes is how to sync the profiles across the cluster. When we talk about running a container with some specific AppArmor profile, the AppArmor profile or SELinux profile should exist on the worker nodes. And when you have no clue where the application is get deployed, you need a way to sync the profiles across the cluster, across all the nodes. It's not easy to do that manually, and the KubeArmor project do that for us. It's automatically get your definition translated to the available LSM module profile, and then spread it across all the nodes within the cluster. In addition to translating your definition into the profile, KubeArmor uses eBPF for observation and monitoring. So it's able to provide you a way to check what's going on within the application. I've got a couple of examples. So this is the main architecture. You have containers, VM, or Kubernetes cluster. You define the policies. In YAML files, it goes to the KubeArmor, and then KubeArmor translate that into AppArmor, BPF, LSM, and SELinux. And then it provides you some telemetry and alerts. And this one is internal architecture of KubeArmor. We have KubeArmor daemon set, which is the heart of the system, and it provides us an init container, and within the init container, it comes up, it compiles the eBPF code to monitor all the system calls, and it needs an init container because the compiling process depends on your kernel. And when the eBPF code is ready, the bytecode is ready, the main container is up and running, and it gets started, detects your available LSM module. It creates a gRPC endpoint for collecting the logs and syncing the defined policy within the Kubernetes through the standard CRDs. And it's the actual container work with Seccomp and AppArmor or SELinux or BPF LSM or any other security features to restrict the processes. On the other hand, we have the KubeArmor relay server, which is the point aggregate all the logs, metrics, alerts into a single point to allow Prometheus, Elasticsearch, and other monitoring tools to aggregate and fetch the logs from a single point. And on the other hand, we have a KubeArmor controller, which provides us a mutating webhook, and it automatically adds Seccomp profile, LSM profile, even the developer needs to provide a proper profile. In the case of BPF, LSM, and AppArmor, if I try to compare them, when try to use a kubectl exec command, when you provide an AppArmor profile for your application, you can check that. For example, if I get back to this example, I deny the sh command. But with this profile, if you try to do the kubectl exec command and try to execute sh, the system allows you to execute the sh command. It's because the immediate child is not enforced by AppArmor. But when we use the BPF LSM, it denies when you try to use the kubectl command, the exec command. When you have no BPF LSM available within your system because of the kernel version, the solution is to use OPA gatekeeper and restrict the container to be able to execute the command directly. So you need to enforce a policy with OPA and deny the user to directly execute the command you don't want to be executed within kubectl exec. And then allow the user, for example, to execute sh first, and then execute the cat command, for example. In the case of rules, the BPF LSM, as mentioned, is deployed using the codes. It provides the full enforcement in the case of network rules for the deployment and prevents when the allow privilege escalation is set to false. And for the other thing, the generated alert is based on the block. The eBPF base for the AppArmor is completely different and is matching based on what's going on in the application. And the next thing is, even though you do not define any profile, any AppArmor profile, KubeArmor itself provides a default profile which denies the application and the container from accessing dangerous assets within the system. For example, it doesn't allow the process to access the pros directory, the pros mount point, and it doesn't allow the process to get to the security features your Linux provides at the moment. And this is another example. If you want to use the KubeArmor policy, we have to define something like this. I define a policy to block access to these files, the passwd and shadow file, and prevent the container to execute apt command and apt-get command, and it's automatically translated to this profile and get applied, and it mutates your container. And this is the log output. It shows you the cluster name, host name, pod name, and the result of what's going on, the action, and everything related to the output of the system, the result of what's going on, and what happened in your platform. If you want to learn more, check it out, the Kubedemy.io. And at the moment, you can enroll to our container security workshop using 50% discount today and tomorrow using KCD UK 2024. Thank you.